Welcome again in the course module of communication engineering. So in the last lecture, we have seen the bit rate and bandwidth requirement of our PCM system. So as I said in the last lecture that we have to look at another topic which is called as the signal to quantization noise ratio of PCM system. So to start with the signal to quantization noise ratio for PCM system, we have to first build up a concept related to a random variables. So today, before starting the topic of signal to quantization noise ratio, I would like to first explain you what is random variables, because this concept has to be used while discussing the or calculation of the this result of signal to quantization noise ratio. So let's see first of all what is this random variables, because this topic is important. So first of all, this a topic like random signal theory, okay, it has to be discussed separately, but because I was teaching pulse code modulation, and we have to perform the noise analysis, okay, continuously. I wanted to make this topic, so that's why I'm discussing this particular random variable topic in this lecture. Okay, so only few things I will discuss about this random variables which is necessary to discuss the signal to quantization noise ratio calculation. So first of all, you try to understand what is random signals. Okay, in my previous lectures, okay, basically in the beginning of this particular course, I explained you a different class of signals in which I told you that there could be a signal which is known as the random signals or deterministic signals. Okay, so I'm just repeating again what is random signal and what is deterministic signals. So basically all those signals which are having its known mathematical form, okay, and it's either its mathematical form is known, or it may be its graphical form is known. So meaning is that by having this idea, okay, either graphical form or mathematical form, we can exactly predict the future value or future behavior of this signal, okay, and that signals will be known as the deterministic signals, okay. But in case of the random signals, I said that in the case of random signal, it doesn't have any mathematical form, okay. We cannot represent it by a certain mathematical expressions. Even it doesn't have any a certain graphical form that can be used for prediction of its future values. So basically what we mean to say a random signal, the random signal are those signals whose value cannot be ascertained in futures, okay. We cannot decide what will be the value or exact value of this signal is going to take in futures, because its mathematical form is not known. So even in case of speech signals that we generate, okay, if we talk about the human speech signals, then generally the human speech signal is also a random signal. It is not a deterministic signal, because if you see its waveform, you will find that a very haphazard, very random kind of variations in the output of your like mic you will get, okay, and that particular values you not be able to predict, because nobody knows that the speaker is what he is going to tell, and with how much intensity he is going to tell, okay, what will be the his own tonal quality, okay, and therefore we cannot decide what will be the waveform that he is going to generate. So therefore it is also comes in the category of a random signal, okay. So in communication we do have random signals, okay. Most of the signals are random in nature only, okay, and therefore we need to have idea of the random signal theory. So let's start with this particular topic, random variable. So as I written here, you can see what is the random variable we mean to say. It is defined as the process of assigning a numerical value to the outcome of an experiment. Okay, so what does it mean to say that it is a defining? It is defined as the process of assigning a numerical value to outcome of a particular experiment. So let us suppose that if we consider like one of the experiment, you can say, or let us suppose we are conducting one particular event. For example, if I tossing a coin, okay, just to take a simple experiment like tossing a coin. Okay, so generally when we toss the coin, we know that the coin is having two different faces. It is having a head and tail. Okay, one face is having head and another phase is called as tail. Okay, so once we toss a coin, a person cannot be certain that due to this tossing of the coin, whether the face that will come is head or tail. Okay, we cannot ascertain. Okay, because the probability of our coming head and tail is equal. Okay, so both they are having its probability equals to 1 by 2. So similarly, even if we consider like rolling a dice. Okay, so we know that in the dice we are having total 6 faces, and the numbers will be written like 1, 2, 3, 4, 5, and 6. So this way we are having the dice. Okay, so whenever we are rolling a dice, still because of there are total 6 faces, which particular face will come upward, that we cannot determine very specifically, because there are total 6 possibilities. Okay, so in the case of tossing a coin, there are 2 possibilities. In case of rolling a dice, there are total 6 possibilities, and therefore we cannot ascertain, but only we can say that there is a certain probability that this particular face will come up. For example, there is a half probability that the head will come when we toss a coin, and similarly there is a half probability that a tail will come onto the face. Okay, so that will be the outcome of this particular experiment. Okay, so basically, if I say the outcome of this particular tossing a coin or rolling a dice is represented by capital X. Okay, so this capital X is actually denoting the probability that this particular X is going to take. Okay, for example, if it is head, what is the probability that it is going to take the head? Okay, so basically what I am saying is this random variable is the outcome of an experiment. Okay, outcome of an experiment, and because it is a random thing, okay, we are not ascertaining it. So what we are saying that whenever any outcome is assigned to a particular variable, that particular variable is known as the random variable. For example, let us suppose first we have to talk about these two things. Okay, like probability distribution function or cumulative distribution function. This is the other name of the probability distribution function. So first you try to understand that, you will be automatically come to know that what is random variable. Okay, you will automatically understand this. Okay, so first if you see what is probability distribution function or cumulative distribution function, then basically this probability distribution function will be in short form it is written as capital PDF. Okay, or it can also be represented as capital CDF. Okay, so basically this probability distribution function is actually defined in this way, like capital F capital X in bracket of X. So what this function represents, that we have to understand. Okay, where you remember that this is this capital X denotes the random variable. Okay, this particular capital X denotes the outcome of an experiment. Okay, whatever the experiment we are conducting, this capital X represents that outcome. Okay, so this outcome can be anything. Okay, all possible outputs it can assume. So basically this represents the outcome of random variable, and this small x represents that for a particular experiment when we conducted uh, the outcome of that particular experiment. For example, this capital X represents all the outcomes. Okay, you remember that this represents these, this is a random variable, and this represents all the possible outcomes. Okay, and here small x represents the only one experiment that we have conducted. Then for that particular experiment, what is the outcome? Okay, so what does it mean that if we write F capital X and X, then this represents what is the probability that our random variable capital X is less than or equals to X. Okay, what is the probability? So what is the probability that this particular X is less than or equals to X? The meaning is that if we write F capital X 10, the meaning is that what is the probability that this random variable capital X, which is denoted by capital X, is less than or equals to 10. So this is what the meaning of probability distribution function. So now we can elaborate it by with this help of a particular example. Let us suppose that if we consider rolling a dice experiment and the random variable X represents the outcome of the experiment. Okay, then you can see that what are the outcomes of the experiment are possible. So if we represent all the outcomes with the random variable capital X, then the possible outputs will be 1, 2, 3, 4, 5, 6, because we know that there are total 6 faces, and these 6 numbers are actually written on those faces. So we are having this total 6 outcomes which are possible. Now, if these are the total 6 outcomes, then we can write what is the probability of getting these outputs. Okay, what is the probability that this particular output we are going to get? So as we know that this all the outcomes like 1 to 6 are equiprobable. Okay, it is equiprobable. So it is having the same probability. So because there are total 6 possible outcomes, okay, then coming output of this particular experiment, outcome of this particular experiment, like x equals to 1 is 1 by 6. Similarly, for x equals to 2, again it will be 1 by 6. And for all these other outcomes, this probability is going to be 1 by 6, because all the events or all the outcomes are equiprobable. Okay, it is equiprobable. So therefore, the probability of getting this particular outcome, okay, is equals to 1 by 6. So what we are writing, it is the probability that this random variable is coming out as equals to 1 in a particular experiment. Again, what is the probability that we are getting to is again 1 by 6, and so on. So now we have to sketch the probability distribution function PDF. Okay, so now to try to see this, if we have understood this one, okay, what are the probability that this random variable is going to take the output equals to 1 to 6. These are the 1 by 6, 1 by 6, and 1 by 6. Now you try to see this probability distribution function. So let us suppose if we write this probability distribution function fx in bracket 0.1, it meaning is that what is the probability that the random variable x is going to take values which are less than equals to 0.1. So you try to understand that in this particular experiment, this random variable is a discrete variable, okay, because the random outputs which are possible is 1, 2, 3, 4, 5, 6. Okay, there is no output like 0.1. Even we do not have any output like 0.99. Okay, so the only output which is possible is equals to 1. Okay, and after 1 it is directly 2, then 3, then 4, and 5. So we do not have any output in between 0 to 1, or in between 1 to 2, or 2 to 3, then 3 to 4, 4 to 5, and 6 greater than 6. Okay, so if we want to write this particular probability, what is this probability that this random variable x will be less than or equals to 0.1, obviously the answer is equals to 0, because there is no such probability. When we rolling a dice, we are going to get onto the faces like 0.1, because there is no 0.1 written on any of the faces, and therefore this output is equals to 0. Similarly, if we write what is the fx 0.99, so this is represents our probability distribution function. So it means that what is the probability that this random variable x will be less than equals to 0.99. Again, the minimum possible output is equals to 1. Okay, so therefore again this particular output is equals to 0. There is no such probability that any of the phase will get the output equals to 0.99. Okay, in the case of rolling a dice experiment. Similarly, what is the probability that fx equals to 1? So the meaning is that what is the probability that x is taking the value which is less than or equals to 1. So we know that for less than 1 there is no probability, but for px x equals to 1 we are having a probability equals to 1 by 6, and therefore we can write the probability for fx1 is equals to 1 by 6. Okay, similarly, if you want to write what is the probability fx 1.8, the meaning is what is the probability that x is taking value which is less than equals to 1.8, and therefore we know that there is no probability. Okay, I mean to say that x is less than equals to 1.8. Okay, so we know that there is no such thing like 1.8 onto the faces, but if you see in this expression, it is x is less than or equals to 1.8. So less than 1.8, so 1 is less than 1.8. So what is the probability that we can get this 1 is equals to 1 by 6. So therefore, the probability that the random variable x will take this value less than equals to 1.8 is also equals to 1 by 6. Okay, so now if you write probability x equals to 1.8, again this value is equals to 0. You try to understand the difference between the two. Okay, because here we are writing that the probability that x exactly equals to 1.8. Okay, so x can never assume this value 1.8 because 1.8 is not an possible outcome of rolling a dice experiment, and therefore the probability of getting x equals to 1.8 is equals to 0. But here in this case, when we calculating the probability distribution function, then this represents x is less than or equals to 1.8, and because 1 is less than 1.8, and therefore this probability is coming out as equals to 1 by 6. So now when we calculate fx equals to 2, okay, it means that what is the probability that x is less than equals to 2. So obviously that time we have to add this 2 probability, because less than and equals to 2. So this 1 by 6 again plus 1 by 6. So that is going to be giving you value equals to 2 by 6. And therefore that probability will become 2 by 6. So now once we understood this probability distribution, now what we can do is we can sketch the probability distribution function. Okay, so how to do this graph is, first we have to take the random variable onto the x-axis, and then we have to plot the probability distribution function fxx. Okay, so now you try to see this function when the random variable was less than 0. Okay, less than 1, sorry. So when this random variable x was less than 1, okay, you can see that there is no such probability that the output will be less than 0. Okay, so obviously in the rolling a dice experiment we cannot have this output or outcome which is less than 1, and therefore this probability is equals to 0. Once this x is becoming 1, okay, at that point this particular output or the outcome becomes 1 by 6. So what is the probability that x equals to 1 is equals to 1 by 6. And now this probability will remain same until we get x equals to 2. So once we are getting x equals to 2, it will be remain same, it is 1 by 6. As we can see, even here it is fx equals to 1, it is 1 by 6. For fx 1.8, it is again equals to 1 by 6. So it will be remain 1 by 6 just before 2. Once we are x equals to 2, this value is going to increase by 1 by 6, and then the probability of getting fx 2, that means probability that x is less than equals to 2 is 2 by 6. Similarly, when x equals to 3, this is going to be 3 by 6. When it is 4, it is going to be 4 by 6. Then 5, when it is 5 by 6. When it is 6, it is going to be 6 by 6. So you remember that if we write like fx6, the meaning is that what is the probability that the random variable x is less than equals to 6. So basically in all the experiments, okay, all the numbers 1 to 6 are actually less than and equals to 6. Okay, and therefore any of them may become like either it may be 1, 2, 3, 4, 5, 6. So all these numbers are the possible outcomes, and therefore the probability that we are going to get is equals to unity. So here you can see that at 6, okay, we are going to get this probability distribution function value is equals to unity. So this way we can plot our probability distribution function. So here we are going to get the maximum probability is equals to 1. Fine. So similarly, if we want to just take another example, let us say we want to have we conducting an experiment related to tossing a coin. Okay, so let us say a coin is tossed twice. Okay, then a random variable x here represents the number of heads. Okay, number of heads. So basically the same coin is being actually tossed twice. Okay, so basically what we can have is the outcome of means tossing the coin twice. It may be tail, it may be tail and head, it may be head and tail, and it may be a head and head. So basically what is this x represents? This random variable represents the number of heads. So here you can see that in the first outcome, if both the times when we tossing the coin, if the outcome is tail and tail, so there will be no heads in the output, and we can write x equals to 0. Okay. Then similarly, in the second time, we can see that it may be the first time the outcome of tossing the coin is tail, and the next time it is head. Okay, so how many heads we are getting here? We are getting one time head. Okay, similarly there can be the possibility that while tossing the coin, the first time we get the head and the second time we get the tail, and then the outcome again we are getting one head. There may be a possibility that both the times we can get the heads. Okay, so we are having x equals to 2. Okay, so now basically this represents our possible outcomes of our experiment. Okay, so number of heads which is possible is either 0, or it may be 1, it may be 2. So we have this random variable, and the possible outcome is either no heads will come in the experiment, it may be one head come in the experiment, or it may be two heads may come in the experiment. So as we know that while tossing a coin, uh, either head or tail will come, and the probability of coming this head and tail is equiprobable, and this probability is 1 by 2. Okay, so because tossing a coin twice, it is an independent experiment. Okay, it is an independent event, and therefore if we want to calculate what is the probability that there will be no head that will come out of this experiment, then coming as a tail is 1 by 2. Okay, this is the probability. Then this probability has to be multiplied again with the 1 by 2, and then we are going to get this probability equals to 1 by 4. Similarly, in this case, here we have this probability, here we can have this number of head is equals to 1. So again, this probability of coming like tail and head is 1 by 2 and 1 by 2. So this will be coming out as 1 by 4. Again, for head and tail, this probability is 1 by 4. So if we add them, we can get this probability that will be equals to 1 by 2. Okay, so now again when this is head and head, again the probability that we are going to get is 1 by 4. You remember that addition of this all the probability should be equals to 1. Okay, so maximum probability is possible equals to 1. So now what we can do is we can plot this particular distribution. Okay, with respect to the random variable x. So let us suppose this is our random variable x, then getting a 0 heads. Okay, getting a 0 heads is having a probability equals to 1 by 4. So that has to be represented by 1 by 4. Then probability of getting the one head. Okay, one head, fine. So this one head, so you remember that we have to plot fx1. Okay, so fx1 means probability that x is less than equals to 1. So what is the less than equals to 1? So it is 1 by 4. Again we have to add 1 by 2 to it. Okay, that will be giving you the value equals to 3 by 4, and therefore this value is making a jump, and then we are getting this result equals to 3 by 4. Again, when x equals to 2, we have to add again a half to it, and then this value will be 1 upon 4 to it, then this value will become 1. And this way we are able to plot this PDF graph. So I hope you must be able to understand how to plot this probability distribution function curve. Okay, so this way we are actually calculating the probability distribution function or cumulative distribution function. So now you try to understand that based on these two cases, we can have the properties of the probability distribution function. So what is the probability that these fx x is actually having its range in between 0 to 1? In all the cases, you can see that this fxx is actually varying between 0 to 1. Even in the last case, we had this value equals to 0 and then 6 by 6. That is because it is representing the probability of this random variable x. Okay, so therefore this probability will be in between 0 to 1. Similarly, if we want to calculate fx infinity, the meaning is that what is the probability that the outcome x is actually less than equals to infinity. So obviously that will be having a probability equals to 1. Okay, it is a probability because obviously an experiment is going to have any particular output. Okay, and because anything equals to and less than infinity means it is covering all the possible outcomes. Okay, and therefore this probability has to be equals to 1. Similarly, when we calculate fx minus infinity, then this represents that what is the probability that the random variable x will be less than or equals to minus infinity. So it is not possible to go less than minus infinity, because minus infinity is the extremist point. Okay, it is the extreme point. So we cannot have any x value which is less than minus infinity. and therefore this probability is equals to 0. Now, similarly, if you wish to calculate the probability that this random variable is in between x1 and x2, okay? So let us say that we want to calculate this probability that what is the probability that this random variable is greater than x1 and it is less than equals to x2. Then the same thing can be calculated by having this particular expression of our PDF, okay, probability distribution function, which is fx x2 and minus fx x1. So this particular function, you can see that this actually represents what is the probability that this random variable x is less than equals to x by 2, and this represents what is the probability that the random variable x is less than equals to x1. So in the previous case, if you see the rolling dice experiment, okay, if let us suppose if we take p equals to like 2, let us say this x1 is 2 and this capital X and this x2 is equals to 4. So let us suppose we want to calculate this particular probability in the case of rolling a dice experiment. So here we can see that if we want to calculate from this formula, okay, how it can be calculated is first we need to calculate fx x2. So what is the probability that this random variable is less than x2? Means it is less than 4, okay, so less than 4. So here you can see that from this less than equals to 4, so here you can see that this is the probability that this random variable is having its probability less than equals to 4. It is 4 by 6. Similarly for 2 it is 2 by 6, okay. So this can be written as 4 by 6 minus 2 by 6, that will be equals to 2 by 6. So this way we can calculate what is the probability that a random variable can take in between any range, okay. Similarly, if you want to calculate that what is the probability that this random variable x is greater than x1, okay, is greater than x1, then obviously the same thing can be calculated by 1 minus fx x1, okay. So for example, if we want to calculate what is the probability that this random variable x is greater than 4, okay, what is this probability? So you just see that what is the probability? So there are only two possible outcomes like 5 and 6. So what will be the probability? So it is 1 by 6 plus 1 by 6. So the output, the probability will be equals to 2 by 6. Okay. So for this, we are going to get 2 by 6. So the same thing can be calculated by subtracting this particular thing, 1 minus fx x1. So the meaning is 1 minus fx4 we can write. So fx4 is having its probability equals to 4 by 6 as just we see it. So 1 minus 4 by 6 will giving you the value equals to 2 by 6. Okay, so both ways we can calculate. Okay, both ways we can calculate. So we are getting this particular result 2 by 6. Similarly, if we want to calculate the probability that a random variable x is exactly equals to x1. So how we can calculate this? So first we have to calculate what is the probability that x is less than or equals to x1, then minus we have to calculate what is the probability that x is means x is less than equals to x minus. What is this x1 minus represents? X1 1 minus represents a small decremental value in the random variable x. Okay, so for example, if we want to calculate probability that what is the probability that the random variable x will be equals to 2, then that can be calculated by having fx2 minus fx, a small decremental value in the random variable, so that will be 1.999. So in the previous case, you can see that this particular probability fx2 is equals to 2 by 6. Okay, and the probability of one means getting 1.999 is equals to 1 upon 6, and therefore the probability of getting x by 2 is equals to 1 by 6. So you try to understand this whole discussion. Okay, one more property that this probability distribution function is having is that it will always be a increasing function of x. You remember that it will always be an increasing function of x. You can see that it is an increasing function of x. Okay, so here in this case it is a staircase functions. Okay, but it is not always be necessary that it should be a staircase functions. So here you remember that in both the examples, the random variable that I have taken is our discrete random variables. So why it is a discrete random variables? Because the outcome of one particular experiment is actually a discrete outputs. For example, in tossing a coin, we are just having head and tail. Okay. Similarly, in rolling a dice experiment, we are just having numbers like 1, 2, 3, 4, 5, 6. But we do not have any range like in between 1 and 2, there will be a certain output. Okay, a discrete outputs are only possible. So the outcomes are only assuming a discrete values. Okay, it is not taking any continuous values. So in real life, there may be a possibility that the random variable could be a discrete random variable, or it can be a continuous random variable. Okay, in which we can have a continuous output, okay, from a particular experiment. Okay, so now one more thing that we have to look at is about the probability density function. Okay, so at present, in the previous discussion, we have seen what is the probability distribution function. Okay, and now we have to look at what is probability density function. Okay, you remember that that was represented by capital PDF, and this is represented by a small PDF. Okay, so you please do not confused with these two things. Okay, it is probability density function, and then it was probability distribution function. Okay, so you try to see that in the case of PDF, okay, probability density function, it actually indicates the distribution of total probability to various random variables. Okay, so mathematically it is actually related by this particular expression, and it will be represented by a small f, a capital X x, and that will be equals to the differentiation of the probability distribution function fx(x). Okay, so this way it is defined. Now you try to see what this probability density function represents. Okay, so if you see in the previous case, we had this particular sketch in the case of rolling a dice experiment. Okay, onto x-axis we had the possible outcomes. Okay, these are the random variables, so, and these are the possible outcomes of the random variables, and then this represents the probability distribution function. So basically, when we perform the differentiation to this particular fxx, we know that whenever there is a spike at this point, we are going to get a delta function. Okay, at 1 we are going to get a delta function, then again at 2 we are going to get the delta function, and accordingly, whatever be the height of this particular step, okay, the same height will also come for the delta function. You remember that. So we know that it is all the outcomes are equiprobable. Okay, so this step size everywhere it is equal. Okay, and that is equal to 1/6. Okay, so whenever you perform the like differentiation of this particular function, we know that for a constant the differentiation will be equals to 0. Okay, and whenever there is a step change, that step change will have its differentiation equals to a delta function. So here we have the delta function at 1, at 2, 3, 4, 5, and 6. And all these delta functions are having its magnitude equals to 1/6. So now you try to understand what this represents. This represents that the distribution of the probability among all the possible outcomes. Okay, so these are the all possible outcomes, and now this fxx represents all the outcomes are equiprobable, and this the probability is equal to 1/6. Okay, so basically this represents how this total probability 1 is going to be distributed among all the random variables, So similarly, again, we can see from this picture. Okay, so if we have, let us say, any continuous random variable which is defined in this way. Okay, let us say it is defined in between 0 to 10. Okay, it is defined in between 0 to 10. So let us say it is a continuous random variable, and this is representing our possible probability distribution function. Okay, you remember that this probability distribution function will always be an increasing function. Okay, you remember that. This is very important property of this probability distribution function. It will always be an increasing function of x. So this is representing a particular PDF. Okay, so let us say that this is a continuous random variable, and therefore it is changing continuously. Okay, and it is represented by this particular graph. Okay, so if we want to its magnitude up to means when it is x equals to 10, the probability is becoming equals to 1. Okay, obviously when a random variable will take its maximum value, okay, or all the possible values, that time the probability will become equals to 1. So here it is probability equals to 1. So now if you want to calculate the probability density function, okay, then we have to differentiate this particular equation, okay, this particular graph. So if you differentiate this particular graph, how this expression can be written, it is a linear equation. It can be written as equals to y equals to mx. So here m is equals to the slope of this particular curve, and that you can calculate, that will come out as equals to 1 by 10. So this can be written as y equals to 1 by 10 x. Okay, so once you differentiate it, you will be getting the answer equals to 1 by 10. So that differentiation has to be done in this range from x equals to 0 to 10. So between this probability density function will have its value equals to 1 by 10. Okay, so now this will be the differentiation value, and this is our probability density function. What is the meaning? The meaning is that for this particular probability distribution function, okay, the corresponding probability density function is uniform. Okay, it is uniform. The meaning is that, again, the possibility of all the outcomes are equiprobable. Okay, whatever be the values this random variable is going to assume in between 0 to 10, all the values are equiprobable because it is having its probability equals to 1 by 10. And this will be the distribution. Okay, this will be the distribution. So in between 0 to 10, it is having its probability equals to 1 by 10. Now you can see that if you multiply this probability 1 by 10 with this particular axis 10, okay, means its width and its height. Okay, if you multiply with both these values, this product is going to be out, means this product or the area under this curve is equals to unity. Okay, that you can calculate. Okay, 1 by 10 multiplied with 10, that will be coming out as equals to 1. So obviously total, because this fx x represents the distribution of the total probability. Okay, so once you multiply or if you calculate the area under the curve of your probability density function, that will be going to give you total value equals to unity. Okay, so this is our probability density function, and how to there are certain properties of this PDF that we need to understand. So basically what we can have is, if we have any probability density function which is fxx, it is defined by fxx, then if we integrate this from minus infinity to infinity, the area under the PDF curve is always giving you value equals to unity. Why it is giving unity? Because it is representing the total probability. Okay, total probability. So because probability, the maximum probability possible is equals to 1, so when we calculate the total area, this value is going to be equals to 1. Similarly, if we want to calculate this particular integration minus infinity to x1, okay, minus infinity to x1 fxx dx, then this can be calculated by calculating this. This is similar to calculating fx in bracket x1. Okay, so why? Because this represents that what is the probability that the random variable x is less than or equals to x1. Okay, because we are integrating this probability density function from minus infinity to x1. So the meaning is that we are just calculating that particular probability which is less than x equals to means your x is less than x1. Okay, or less than or equals to x1. So basically this represents the probability that this random variable x will be less than or equals to x1. Similarly, if you want to calculate this particular means integration x1 to x2 and fxx dx, then obviously again it can be calculated by calculating the fx x2 minus fx x1, and that will be giving you this value p means which is similar to calculating this particular probability. So it is fairly straightforward. Okay, you can understand this formula directly. Okay, it is not much thing to discuss in this expressions. You can directly understand. Okay, it is a simple integrations. Okay, and by calculating this integration, the same integration can also be calculated by having this formula for probability distribution functions. Okay, let's see this things from this particular example. Okay, let us suppose that we have a continuous random variable which is uniformly distributed in the interval of 0 to 10. Okay, so first we try to understand what is this question is. So the question is, a continuous random variable is uniformly distributed in the interval of 0 to 10. Okay, so it is uniformly distributed. So first of all, what is this value means? Let us suppose that the random variable is equals to x. Okay, the random variable is equals to x. So it is saying that it is uniformly distributed in the interval of 0 to 10. So basically uniform distribution means it is giving you the probability density function. Okay, it has provided in this statement, it has provided the probability density function. It is in this statement. Okay, because it is saying that a continuous random variable is uniformly distributed in the interval of 0 to 10. So this is our suppose that we have the random variable equals to x. So in between 0 to 10, it is uniformly distributed. So it is uniformly distributed because it is a continuous random variable. So we have to make it means a continuous line. So it is distributed uniformly. And let us suppose that this magnitude is equals to a. Okay. The magnitude is not mentioned. So let us suppose that this particular magnitude is equals to a. So first of all, we need to calculate what is the value of a. So how to calculate this a? So we need to first follow the property 1. Okay, what is this property 1? This property 1 says if we integrate the PDF, okay, so area under the PDF curve is equals to 1. Okay, so you can directly calculate the area of this particular curve, and that area will be 10 multiplied with a, and that will be equals to 1. So you can directly get a equals to 1 by 10. Okay, or you can do this integration because this a is defined for 0 to 10. So this integration will be done for means in this range of 0 to 10. So 0 to 10 a dx, you will be getting this probability equals to 1. So you are going to get a equals to 1 by 10. So this way we are going to calculate this value of a. So once we have calculated the value of a equals to 1 by 10, we can sketch the PDF. So this is our PDF, and here a value is equals to 1 by 10. Now we can calculate the PDF. Okay, this small PDF was your probability density function, and this capital PDF is representing our probability distribution function. So how this can be calculated? By doing the integration. Okay, by doing the integration. So you just because this 2 is related with the differentiation. Okay, this is related with the differentiation of the PDF, capital PDF. Okay, so we have to integrate this function to get the probability distribution function. So this is our constant. So if you integrate it, you are going to get this linear line, and obviously this magnitude will become 1, and this is going to up to 10. So this is straightforward to calculate. You can calculate what is the PDF and capital PDF. Okay, now if you want to calculate this probability, that what is the probability that this capital X is less than equals to 1. So suppose if we want to calculate this particular probability, okay, then this probability we can calculate by having this second property. Okay, so what this second property says, if we want to calculate any probability which is x less than equals to x1, okay, less than equals to x1. So here it is probability that x is less than equals to 1. So that can be calculated by integrating it from minus infinity to 1. Okay, it is minus infinity to 1 fx x dx. Okay, so simply because we already have the form of fxx. Okay, this is already known to us. So this particular graph is actually exist in between 0 to 10. So this lower limit will become 0, and this will become 1, and this is 1 upon 10 dx. So this probability you can directly calculate, that will come out as equals to 0.1. Similarly, if you want to calculate the probability of x in between 5 to 8, okay, again you can follow the same rule. Okay, you just integrate it in between 5 to 8, and our fxx value will be equals to 1 upon 10 dx. So you can calculate this probability will come out as equals to 3 by 10. Okay, again you can calculate the probability. What is the probability that x is greater than 9? So how to calculate? Again you can write this particular expression. Okay, you can just write this particular expression. Okay, and that way you can calculate the any probabilities. Okay, you can calculate any probabilities, so that you can calculate directly from the given probability density functions. Okay, so I hope you must be able to follow these two things. Okay, probability distribution function and probability density function. Okay, you remember that the random variable actually denotes the outcome of any experiment. Okay, any experiment that we conduct. So whatever those outcomes, if we assign to a particular variable, is called as the random variable. Okay, and the random variable can be a discrete random variable, it can be a continuous random variable. So if outcome is discretized output, okay, then it is a discrete random variable. If it is a continuous output, then it will be a continuous random variable. So I will discuss a few more points about the this random signal theory, which is necessary in the coming lectures. So thank you for watching this video. If you have any further doubt, let me know with your comments. So stay connected with the channel for more updates.